Hello there. Thank you for watching Differential Questions by Alex. That's me. All right, so again, we're going to continue the topic about linear differential equations. And again, we are focusing on only homogeneous differential equations. And more specifically, we are dealing with linear independence. All right, so let me go back and tell you the outline. So we are under the category of homogeneous differential equations. And then we're going to talk about linear independence here today. A short topic, but I want to kind of separate all the ideas so that way it doesn't get all cluttered into one single video and it gets overwhelming. All right, so I have a definition here, and if it doesn't make sense after I read it, don't worry. I have a few examples that I'm going to use to help change this definition into something more manageable. All right, so this means, so before I give you the definition or read the definition, I want to say that the type of differential equations that we were dealing with were something like this. So a double prime plus by prime plus cy is equal to 0. And so here the n is, in the specific example on the top, is n is equal to 2. But you could have maybe a third derivative, so 1, 2, 3, and then the d is supposed to be a function also. Or maybe you could have another, so maybe a f multiplied by y to the fourth derivative. Okay, so it can be a very lengthy differential equation. And for the most part, in this semester, we are going to focus on the second order differential equations. But a lot of the things that we are dealing with a second order also are true for third order, fourth order, and then any other number that you want to here. So anyways, so that's a little bit of comment here, and then that's why I have this definition that seems a little bit more lengthy than what we were dealing with last time. Last time we were just dealing with a second order, but here we're dealing with just an arbitrary order. Could be 2, could be 3, could be 4. All right, so you have a collection of functions, and if you make the linear combination of the functions, and if you can choose, if the linear combination is equal to 0, what we're saying is this, then the numbers have to be equal to 0. Okay? So again, like I said, if the definition doesn't make any sense, let me go into the specific examples to kind of give you a different definition that is equivalent, that is essentially the same, but just worded differently. So here, and one comment that I want to make is the following. At the moment, we don't have any differential equations to think about here in this problem, in this type of problems. So this is just a purely algebra / function type of problem. So there's no differential equation here. So we just have a collection of 4 functions, and then we want to talk about the idea about linear independence or linear dependence. And so what that means is the following. The idea is this. If you were to write down c1y1 plus c2y2 plus c3y3 plus c4y4, can you choose? So I'm changing the definition a little bit, which is equivalent, but I'm changing the definition a little bit. And so let me actually write down the functions that we have here. So c1 cosine square of x plus c2 sine square of x plus c3 secant square of x plus c4 tangent square of x is equal to 0. So this is the linear combination of the 4 functions that are given to us. Okay, and now the question is this. The question that I want to ask you is, can you choose a specific values for c1, c2, c3, and c4 such that the entire thing will be equal to 0? But the catch is this. Not, let me just write it out here. Not all c's equal to 0. Okay. So can you choose c1, c2, c3 where not all of them are 0? Maybe one of them is 0, maybe 2, but not all of them are 0. Okay. Can you choose c1, c2, c3, c4 such that the entire thing will be equal to 0? But the catch is that all the c's cannot be 0. Okay. Can you do that? Can you do that? All right. So now I'm going to write down some identities that we have seen back in middle school or high school. So do you recall that cosine square of x plus sine square of x is equal to 1? So that's an identity that we're going to use. Notice that that's kind of what we have here. Okay. Another identity that I want to use is the following. So 1 plus tangent square of x is equal to secant square of x. Okay, so this is another identity that we also want to use. Okay, so suppose that c1 is equal to 1, c2 is equal to 1, and then c4 is equal to 1. Okay, so what does that c3 will have to be? Okay, so think about it. What does the c3 have to be? So -1. Okay, so let me write it out, and then you'll see what I mean by that. Okay, so let me write this in gold. So if I make those choices for c1, c2, c3, and c4, I get the following. I get cosine of square plus sine square of x. I'm gonna put down the tangent first. Okay, so the tangent square of x, and then minus secant square of x is equal to 0. So I moved the last two terms, I flip-flop them just for you to be able to see how the identities become. So this thing in the blue box on the very bottom, what is that equal to? According to my first identity, that first blue box is equal to 1. And now we have a tangent square. And what do you know about 1 plus tangent square? So 1 plus tangent square, this entire thing in the blue, that is equal to secant square. And so secant square minus secant square does give you 0. Okay, so those are the good choices for the C1, C2, C3, and C4, such that the linear combination is equal to 0. And then here I want to emphasize that not all the C's are 0, and actually in this case, none of the C's are 0. Okay. Okay. In general, you might have one of them to be 0. If you have 4 C's, then you're allowed to have one of the C's to be 0, but not all 4 of them. Okay, so in this case, we made specifically the choices C1 is equal to 1, C2 is equal to 1, C3 is equal to -1, and C4 is equal to 1. And then with those specific choices, the linear combination is equal to 0. Okay, if you are able to do that, if you are able to choose the different numbers, not all 0, such that the linear combination is equal to 0, then that means that the functions are linearly dependent. Okay, linearly dependent. Okay, the functions are linearly dependent. Okay. So I'm changing the definition that I had in the very beginning slightly because I think it seems a little bit more intuitive this way, but technically I am saying the same thing. All right, so now I want to say one other comment. Okay, here at the very bottom, I have the cosine, the sine square, and the tangent square, and then I have my minus secant square. Okay, so what I'm going to do here is the following. I'm going to rearrange things. So, oops, I was not supposed to erase this. So let me write down exactly what I had before. And so I had cosine square of x plus sine square of x plus tangent square of x minus secant square of x is equal to 0. So I made those specific choices for the c's. And what I want to do here is just a little bit of algebra here. I'm going to move this to the other side of the equal sign. And so I write down cosine square of x plus sine square of x plus tangent square of x is equal to secant square of x. And now I'm going to use the names for them. Okay, so this is actually y1 plus y2 plus y4 is equal to y3. So let me just write it out the other way. So y3 happens to be the combination of y1 plus y2 plus y3. Okay. So we were done with the problem before. We said that the 4 functions that are given to us, and these 4 functions that are given to us, they are linearly dependent because we can write a specific linear combination of them and it equals 0. Okay, we chose the specific values to be 1, 1, 1, and -1 here. All right, so that was the previous slide. And what I'm trying to say here is the following. Okay, so I want to change the definition about linearly independent and dependent to be the following. Here, the y3 is a combination of the previous other Well, actually I wrote this incorrectly. This is a 4 here. What I'm saying is that the y3 is a linear combination of the other functions. Y3 is a linear combination of the other functions. So that is what I mean by dependent. So I think that makes a little bit more intuition, or it's a little bit more clear. If you can make one of the functions in your collection to be equal to the linear combination of the other ones, then that means that your collection is linearly dependent. So let me write that in words for you. Okay. So we have 4 functions, and so this collection of 4 functions is linearly dependent if at least one of the yi's, and in that case was y3, is a linear combination of the other y's. Okay? So y3 turned out to be the combination of the y1, y2, and y4. So if you are able to do that, so you have a collection of functions, and if at least one of them is a linear combination of the other ones, then that means that the collection is linearly dependent. All right, so let me give you another example just to give you a feel for this, okay? So we have 3 functions now, okay? So remember, before we dealt with 4 functions, so we want to know, is that collection of 4 functions linearly dependent? Now we have only a collection of 3 functions, okay? And then we want to know whether this collection of 3 functions is linearly independent or dependent. And what does it mean for the collection of 3 functions to be dependent? According to my last definition, it means that at least one of them is a linear combination of the other 2. And if you look at it closely, let's look at this guy here. So we have y3, this is equal to 2 minus 3x. I can write this down as the following. So 2 times 1 minus 3 times x. And so that means that this is y3, which is equal to 2 times 1 is equal to the y1 function. And then the x is equal to the y2 function. So this is telling us that the third function is a linear combination of the other 2 functions. So that means that the collection of y1, y2, y3, this collection is linearly dependent. Linearly dependent. Okay. All right, so I feel that this definition is a little bit easier to deal with. The only catch is that you have to deal with a little bit of algebra here, and this is not difficult algebra here, but you kind of have to look at the you have to look at the functions, and you kind of have to ask yourself, can I make one of them be equal to the combination of the other ones? In this case, it's a little bit easy, but sometimes they might get a little bit complicated. So I have another example here next that will show you that it's not sometimes so straightforward. Okay. So that's another example here for linearly dependence. So now we only have 2 functions, y1 and y2. Okay, y1 and y2, and then the question is still the same. Is the collection of these 2 functions, so now our collection is smaller, but the question is still the same. Is this collection linearly independent or dependent? Okay, and again, the idea is that we want to look at the combination c1y1 plus c2y2, and then we want to know, can we choose a specific value for c1 and c2 that will make the whole thing equal to 0? Can we do that? Okay, that's one way to answer the question. The other way would be, is y2 equal to some number multiplied by the y1 in this case? Okay, so is that the case? So I'm gonna work with this guy. Okay, and then we can kind of work with backwards to the linear combination. So notice that the y2 is equal to sine x cosine x. Okay. So now I'm going to do something tricky here. So not to scare you, but like to show you what we sometimes have to do. So would you agree that this is the same thing as 1/2 multiplied by 2 sine x cosine x? Okay. So I haven't changed the y2. All I've done is just multiply by 2 divided by 2. So I haven't done anything here. But now this is the tricky part. This is where I'm going to use my trig identity skills. Okay, my math skills on trig identity. The thing in the blue is equal to sine 2x. Okay, the thing in the blue is equal to sine 2x. Okay, so this is where we're using some trig identities. Okay, and so what we are saying is the following. What we're saying is that the y2 function is equal to 1/2 of the y1 function. Okay, so we're saying that y2 is a combination of the other function, or in this case, it's just a multiple of the previous function. But we're saying the same thing as before. And so that's why we say that this combination of y1 and y2 is linearly dependent. So y1, y2, let me just write down here dependent. But we need to write down linearly dependent. All right, so like what I'm trying to say here is that sometimes we have to be very tricky. So here we have to use a little bit of trig to figure out that the y2 is actually a multiple of the y1. In the previous problem, we had to do a little bit of algebra, which was a little easier, but sometimes it's not so straightforward. Okay, so question to you now is there an easier way to answer the question about linearly independent and dependent? Is there an easier way instead of having to do algebra? Something might be easy algebra, something might be complicated algebra, or having to deal with the trig identities, which is not bad here, but we had to kind of look at the pattern. So that is what I'm going to talk about in the next video. There's something called the Wronskian. Okay, so we just finished talking about linear independence, so we give you a feel for what this means. Okay, it means that if it's dependence, if the functions are dependent, then that means that one of the functions is a linear combination of the other ones. And trying to figure that out, you might have to do some algebra, some trig stuff, or some other tricky stuff there. But there is an easier way. And it might not seem so easy when we do it for other problems, but it is the easier way. And then that's going to talk about the Wronskian, but that's going to be for the next video. All right, so that's all I have for today, and I'll see you next time.